Hello, my name is Ahmed Kovacevic. I am the director of the Centre for Compressor Technology at City St George's, University of London. Welcome to this week's Lecture Tuesday. In this short lecture, I will talk about volume index, which directly influences efficiency and reliability of screw compressors. The compressor domain and flow areas in a screw compressor are shown in this image. The dark shaded domains 3S and 3E represent trapped volumes between rotors and the casing, and at the end, and the end of the compression process, respectively. Surface area 7 represents the axial and radial suction ports through which the fluid enters into the rotors, while the gray shaded areas 8 show the discharge port through which the compressed fluid leaves the compressor rotors through the discharge plenum 4 and discharge pipe 5. Volume index is then the ratio of volumes of the working chamber at the beginning of the compression 3S and the end of compression 3E. The green line in the volume versus shaft angle diagram represents the start of the compression process, while the pink line represents the end of the compression. The angle of the end of compression defines the size of the discharge port. The lower the angle, the larger the discharge port, and vice versa, as shown in this image. The largest port is for the volume index VI is equal 1 to 0.5, and the smallest port has a VI of 3. The middle port has the volume index 2. Why does the volume index matter? Let us have a look at the definition of the theoretical compression power shown in equation 1. Theoretical power of compression is function of the gas properties, suction temperature T1, pressure P1, and density ρ1, discharge pressure P2, and theoretical volume flow rate Vt divided by time. Theoretical volume flow rate is function of the machine size and its rotational speed. The ratio of the discharge and suction pressures is called pressure ratio, as shown in equation 2. Relevant gas properties are adiabatic index K, also known as Laplace coefficient or ratio of specific heats, calculated as a ratio of the gas heat capacity at constant pressure Cp to heat capacity at constant volume Cv. The other property is the gas constant R. Using the equation of state of an ideal gas shown in this equation 3, it is now possible to calculate the suction density. For theoretical isentropic compression, pressure at the end of compression P2C depends on the pressure index Pi, which is obtained as a volume index Vi to the power of adiabatic index K, as shown in equation 4. The ideal situation is that the pressure index Pi matches the pressure ratio PR. This is achieved by adjusting the size of the discharge port to the required Bi. Let us examine the PV diagram of an adiabatic oil-free screw compressor, compressing air from 1 to 3 bar. The ideal PI case for this case is 3.03, which relates to volume index of 2.2. The solid line represents the compressor, which has that ideal discharge port, in which case the adiabatic power of compression will be 27.3 kilowatts. The dashed dot line represents the compressor with a larger discharge port with the volume index of 1.5, resulting in PI of 1.76. The discharge port will open earlier than in the previous case, and the gas from the discharge plenum will rush back into the compressor to suddenly increase the pressure in the compression chamber. Further rotor rotation will push the gas out of the compression chamber at the discharge pressure. This is called undercompression, in which case the power consumption will be 29.7 kilowatts. If the volume index is 3, as in the case shown with the dashed line, the compressor will overcompress and the PI will be 4.66. The gas pressure will only reduce once the discharge port is open. The power consumption in this case is 30.1 kilowatt. Therefore, For an optimal efficiency of a compressor, it is important to adjust the port to achieve minimum power consumption. In addition, the increased pressure within the compressor will create high bearing loads, which will reduce bearing life and reduce reliability. Moreover, mismatch in a volume index causes more significant reliability issue for oil-free screw compressors. They are sensitive to the temperature change during compression. Thermal expansion of compressor elements due to the local temperature rise can lead to a contact and compressor catastrophic failure. As it can be seen in this T-alpha diagram, the compressor with a volume index of 2.2 will not exceed a temperature of 140 centigrade. Both compressors with the lower and higher volume index will experience higher temperatures during the compression. In the case of VI is equal to 3, the temperature will reach almost 200 centigrade. Due to the thermal expansion, there is a risk of failure. One would think that the increasing clearances would solve the problem. It will not. The compressor with higher clearances will have higher volumetric losses, lower efficiency, and it will lead to increase in temperature. Such compressor will be obviously less efficient and still experience even higher temperatures and still have a risk of a rotor and casing contact. Similar problems may arise due to a change of gas properties common in industrial processes or gas gathering applications and in refrigeration systems where pressure ratios constantly change. So what do we do? Oil-injected screw compressors have low temperature loads due to injection of oil in the compressor for cooling, sealing, and lubrication. The most common way of regulating volume index of oil-injected screw compressors in industry and refrigeration is to use a radial slide valve driven by the hydraulic system at the discharge of the compressor. Same oil is used to lubricate the slide valve, which changes the size of the radial port while the axial port remains constant. Some oil-injected screw compressors may have a self-regulating VI, which uses tandem slide valve system. However, so far, there are no solutions for regulating VI in oil-free screw compressors where use of oil is not permitted. A novel solution for regulation of VI in twin screw compressors patented by St George's University of London can bring revolution in the design of oil-free screw compressors as it allows automatic regulation of VI by matching pressure index and pressure ratio. It features a set of reed valves installed in an insert between the rotor casing and the discharge plenum with individual reed valves on both male and female rotor sides. Individual discharge valves are activated when pressure in the compression chamber rises to a sufficient level to push a valve into the discharge plenum, while other valves remain closed where that condition is not fulfilled. This self-regulating system ensures that the volume index is changing by the demand of an application. Such systems can also be applied to oil-injected screw compressors. Let's summarize. Volume index defined by the size of the suction and discharge ports is critical for achieving efficiency and reliability of screw compressors. The correct volume index will ensure minimum power consumption, limited increase of a temperature in the compressor chamber, and minimum bearing loads. In oil-injected screw compressors, it can be adjusted by a slide valve that changes the size of the radial discharge port. For oil-free screw compressors, there exists a novel solution with the reed valves, which may bring revolution in design of such machines and the increase in popularity of oil-free screw compressors. With that, we conclude today's short lecture. For any further discussion and questions, please get in touch by email and visit our website for more information about the Center for Compressor Technology at St George's University of London.